This video is on regression analysis. What I'll talk about are scatter plots. I'll look at the correlation, R, and I'll also look at R squared, which true is the square of R, but it's also much deeper in terms of interpreting the R squared than just squaring R. I'll also look at a hypothesis test for the population correlation, rho. I'll look at correlation versus causation, which is a major issue that many people misinterpret correlation by saying that if there's a correlation, then one thing was the cause of the other thing. And we'll find out that that's not okay. I'll also look at residuals, and we'll look at the equation of the regression line and how to interpret that regression line and its equation. So let's start with correlation. So first, when we talk about regression analysis, we're talking about either two survey questions that are quantitative, and we're comparing the answers to those. Whether one goes up implies that the other might go up also, or tends to go up. Or it might be one particular survey question and the date that that particular event happened. It might be that there's two experiments going on, and we want to find out the outcomes of each of those experiments and see if they're related in a linear way. Correlation is a number that describes how close to a line the data lies. In particular, the correlation is always between -1 and 1, and we're going to use the letter R to describe the correlation. So we'll say it's very strong or very weak. In particular, if R is on that left-hand side, if R is equal to -1, then the data are perfectly on a negatively sloped line. If R is equal to 1, the data are perfectly on a positively sloped line. So if R equals -1, what that means is that we know for certain that as one of the variables increases, the other variable must decrease. And similarly, if R is equal to 1, then as one variable increases, the other variable increases also. If R equals 0, then there is no line that is even close to describing the data. I like to kind of think of the night sky. When I look up there, there's just stars all over the place. I don't see a line when I look at those stars. There sometimes could be a pattern and R could still be 0, but that pattern can't be linear. So if R equals 0, we say there is no correlation between the two variables. So let's look at some examples in terms of a number for R and what the scatter plot would look like. So here's the first one. I have the variable x and the variable y, and we can see that the scatter plot, so if we plot the data points, so for every particular survey question, there were two answers, the x answer and the y answer. And if I plot x versus y, we'll notice that with R equals -1, that must mean that these points lie perfectly on a line, and the slope of that line is negative. This does not mean the slope of the line is -1. It just means the slope of the line is negative. And in fact, for this example, we see that the rise is -15, the run is 30. Clearly, the slope is not -1. Let's look at another example. So here's an example where definitely hopefully you all see, that there's a pattern between x and y, because as we can see, there's a parabolic pattern. They lie perfectly on a parabola. On the other hand, there is no line at which these points are even remotely described by. I can try and do this line, or this line, or this line. They're all kind of the same. And R is equal to 0 in this case because it's not described in any nice way at all by a line. Okay, see, here is R equals 1. Very similar to r equals -1, except now the data values all lie perfectly on a line, but the slope of this line is positive. And because they lie perfectly on a line and the slope is positive, r equals 1. In the real world, when we end up with r equals 1, what that really means is that there's a formula that relates the variable x to the variable y. So for example, if the first survey question was how tall are you in inches, and the second survey question was how tall are you in centimeters, then we would end up with an r equals 1 because there is a formula that relates centimeters to inches. And it's a perfect formula. You know how many inches you are, you automatically know how many centimeters you are, and that formula happens to be a line, a linear formula. So whenever you have a -1 or a 1 for r, almost always there's going to be some kind of formula that dictates y if you know x. On the other hand, here's an example where r is -0.93. So notice now the data values do not lie perfectly on a line. They are not far from a line. We can definitely envision a line kind of going along these points, but not every point lies on a line. Also, when we envision this line, pretty solid line, we would envision this line to have a negative slope. And that's why we would guess that r is negative. Let's look at some more examples. Okay, so here is an example also where r is negative, but now it's -0.64. And because of that, what we would see, and we see here, is that the points are even farther from being perfectly on a straight line. You can see that there's a tendency, as x increases, there tends to be smaller y values. But that tendency is not perfect. Notice over here, things go kind of weird. We have small y values and large y values. In fact, from here to here, the y values went up a little bit. So there's a tendency, but it's not a great tendency. It's not that close. Whereas a -0.93, that tendency of going downwards is much stronger. Let's look at some more examples. So here's an example where r is -0.17. For this one, it's hard to even see that there's any kind of relationship of the y value going up or down as the x goes up or down. You just can't see it very well. Notice that r, it is negative, but it's actually pretty close to 0. And when r is pretty close to 0, you kind of have to use your imagination a bit, even to see any kind of tendency. In this case, it's negative. It may be going down a little bit, but it's pretty hard to tell. So I guess if you take enough drugs and psychedelics, you might be able to see that happening, but you need to kind of use your imagination. Let's look at another example. Here's r equals +0.56. So here, the points are pretty spread out. They don't lie in a line that well. But I think without using your imagination too much, you can see that if we have low values of x, they tend to be associated to lower values of y in general, and higher values of x tend to be associated with higher values of y in general. And that's the kind of language that you typically use when we're talking about regression analysis, is things like it's associated with, there's a tendency for. What you don't say is if x is big, y is big. That's way too strong. So let's go on and do one more. And this one is an example where r is 0.90. Here, very clearly, as x increases, the values of y also increase for these points. There's a very clear positively sloped line that is close to most of these points. And you can imagine that line. So that's why r is close to +1. So hopefully with all these examples, you're starting to get a feel for understanding what the letter or the correlation R tells us. So here's a real-life example. What I've got here is actual data, and this is a scatter plot that shows a relationship between carbon dioxide emissions and the year. So let's talk about the correlation. First thing, if we look at this, I think it's clear, to me at least, that there's a very strong tendency. As the year increases, the carbon dioxide emissions have tended to also go up. Notice that's not always true from one year to the next. In fact, if you look at this year, this was the year 2000, and this was the year 2001. Notice that we went forward by 1 year, but the carbon dioxide emissions went down. And that happens. This is real-world stuff. And in fact, if you know your history, in 2001, that's when the 9/11 event occurred. And people stopped flying, people stopped doing long vacations in their cars, and carbon dioxide emissions went down that year. But sure enough, after that, it started trending up again. Notice right here, this was 2008, I believe, and that's when the Great Recession hit, and we had a big drop. If you were to guess R, I would guess that it's pretty strong, because it's a very clear correlation. It's positive, so maybe about 0.9, 0.95, something like that. Later on, we'll see with the computer, you can actually get that number. Okay, so here's another example. This is a table that gives the wins versus salary in millions of Major League Baseball teams. So notice that we have a table very hard to figure out what's going on if there's any relationship between salary and wins when we're given a table. And this is one reason why you draw a scatter plot and come up with R and other statistics, so that we can, instead of just trying to figure out by the numbers, which are really hard to read, we can figure out by graphs and statistics. So here's an important statistic that's going to help us understand. So first, what I did is I drew a scatter plot of wins versus salary. So if I'm giving the salary, I can find out the wins, and we can now see that there tends to be, looks like, a positive relationship. So R is one way of seeing that, but there's another way also, and that's called R squared, which just so happens you can calculate R squared. If you happen to know R, all you have to do is, guess what? All you have to do is square R, and that gives you R squared. So R squared here is 0.51. So let's talk about what that means. So I'm going to read this out, and then it'll be a little confusing, and then let's talk about what it means even to read it. So what this says is sum of the variation in the dependent variable can be explained by the independent variable. Well, sum of the variation in the dependent variable cannot be explained by the independent variable. R squared is the proportion of variation in the dependent variable that can be explained by the independent variable. Now, my guess, hopefully you haven't stopped this video and said, forget it, I don't understand anything, is that this is confusing. So let me explain what that kind of means. There's a lot of measures of variations. The measure that we've done the most often is standard deviation, and that's closer to what this means, but let me use one that's a little easier to understand, and that's range. If you look at the range in wins, and just ignore salary, and just look at the lowest number of wins, which looks like about 66 wins, and the highest number of wins, this looks like about 96 wins. So we can see that there's a total range of values from 66 to 96. That's a range of 30. On the other hand, if I happen to know the salary, so let's say we have a salary just around here, 110, for example, and if we look at this little cluster here, at that salary range, then the number of wins for that salary range looks like it's between, say, 82 and about 95 or so. And that's a range of about 13 or so. And notice that that's close to half of this total range without looking at salary. So if you happen to know salary, then that's going to tell us that we typically are going to have a variation, or like a range or standard deviation, in the number of wins for that fixed salary that's much smaller, and in fact, 51% smaller than the variation that you would have if you didn't know salary, which would go all the way from 65 to 96. So knowing salary really helps us get a handle on what the range of wins are, or the variation of wins. And that's because R squared is pretty big, about 51%. Had R squared been 99%, then that would mean that knowing salary tells you almost exactly what the wins are. Had R squared been, say, 2%, then knowing salary basically doesn't help you at all in trying to figure out what the variation in wins is. So hopefully that makes a little bit of sense. It's a little tough idea, but the upshot is that if R squared is large, then it helps a lot to know X if you want to predict Y. If R squared is close to 0, then it doesn't really help at all to know X if you want to predict Y. So let's move on, and let's talk about hypothesis testing. So first thing, this is not right here, this is not a P. This is a Greek letter, and this is the Greek letter rho, R-H-O. We use the Greek letter rho because that's kind of the corresponding letter for the good old ABC letter R. Just like we use sigma and S, we use rho and R. So rho is going to be the population correlation, and R is going to be the sample correlation. So rho is the parameter for the correlation, and R is the statistic for the correlation. So when we do a hypothesis test, just about always our null hypothesis is that rho, the population correlation, is equal to 0. So that would mean that there is no correlation at all between the two variables. Typically, H1 is that the population correlation is not equal to 0, which means there is a correlation between the two variables. You can also have a rho be greater than 0 if your hypothesis is that there's a positive correlation between the two variables, so as one goes up, the other one tends to go up also. Or you could have rho is less than 0, which means that there is a negative correlation, and that means as one goes up, the other goes down. So in order to run a hypothesis test, we have a requirement that actually is kind of tough to manage, and it's the following. The population values of Y for every individual value of X must follow approximately a normal distribution. That's a tough one. So that means that for any particular value of X, Y must be normal. So in our salary example, that means for any salary, the cluster of wins must follow a normal distribution. Whether the average salary is 10 million or 50,000 or 500,000, all the different teams that have that salary, their wins should follow a normal distribution. And then also, the pair XY were gathered using simple random sampling, or at least approximately simple random sampling. It could be that we use stratified sampling, and that's usually good enough, but you don't want to use convenience sampling pretty much in anything you do in statistics. You need to make this as an absolute necessary piece of data gathering, is you have to use a scientific process. So for the calculator, as we'll see in a little bit, if you want to perform a hypothesis test for rho, then we go to the TI-83 or 84, we go to the stat button, and then you go to the very bottom almost, and it's lin reg t-test. And we'll see that in a little while. The conclusions is typically, as you're used to, if the p-value is less than the level of significance, that means there is statistically significant evidence to reject the null hypothesis and can conclude that there is a linear correlation between x and y. On the other hand, if the p-value is large, we're used to this also, if the p-value is greater than alpha, then fail to reject the null hypothesis and state that there is insufficient evidence to make a conclusion about there being a linear correlation between x and y. So you're used to that. If small p-values, you reject the null hypothesis. Large p-values, you fail to reject. So here's baseball wins versus salaries. And let's find out H0 and H1. H0 is that rho is equal to 0. So our null hypothesis is that there's no correlation at all between salaries and baseball wins. H1, I'm going to let rho not equal to 0. So I want to show that there actually is a correlation between baseball wins and salaries. Another experiment, you might want to see if there's a positive correlation between wins and salaries. So you might think that maybe as salaries go up, the teams tend to win more. So let's use alpha is 0.05. That's standard in hypothesis testing. All right, here's a computer readout. Notice it gives us all kinds of things. The dependent variable was wins. The independent variable was salary. We have the equation of the regression line, which I'll talk about in a little while. And that is that wins is equal to 67.54302 plus 0.16, etc., times the salary. Sample size was 17, if you remember. R was 0.7107. They use capital R for this particular computer program, and it's about 0.7. R squared, we saw, was about 0.51. We saw that a little earlier. Let's not worry about the error standard deviation. The main thing we want to look at is the p-value. And notice that there's actually two p-values written here. There's a p-value for intercept, and there's a p-value for slope. But what I mentioned is that if there's a positively sloped line, or if there's a negatively sloped line that's a good predictor, then that would mean that R is not 0. The only way you're going to get R equals 0 is if there's either no line or a zero-sloped line. And that's R equals 0, or rho equals 0 if we're looking at the population correlation. So it's the slope, and it turns out you can also do a hypothesis test for the slope. And you can say the slope is equal to 0 and the slope is not equal to 0 for your two hypotheses. And you'll get exactly the same p-value. In this case, 0.0014, which notice is smaller. And since 0.0014 is smaller than 0.05, we get to reject the null hypothesis. And the conclusion is that there is statistically significant evidence to support the claim that there is a correlation between the salary of baseball teams and the number of wins the team gets that season. So I want to remind you that does not mean that higher salaries will make a team win more. So let me show you the correct way of interpreting. The correct way is by saying there is a linear relationship between team baseball salaries and total wins. Another way of saying it is as the team baseball salaries increase, the total wins tend to also increase. Notice the word tend. Here's some ways that you should not conclude when you're looking at correlation. We cannot say increasing a team's salary will make the team win more games. See that word will make, or those two words will make? That implies causation. And we can't say that there's any causation for salary and wins. It could be for some other reason that makes both happen. It might be that large salary teams that win a lot happen to be at big cities, and maybe it's the big cities that making them win more instead of the salary. We really don't know. It could be the salaries making them win. We really don't know. You also cannot say a salary increase will result in more wins for the team, because that's another causation, will result. Don't say if you want to win more games, pay your players more money. Another implication of causation, and you can't use causation. So I promised we'd look at the year versus CO2 emissions. So here's the computer analysis for year versus CO2. And if you remember, we saw that R was very strong, 0.97. R squared is the square of that, which is about 0.95. The computer shows us that. Okay, we can also see the p-value for the slope is 0.0001. So there is very strong evidence to conclude that there is a correlation between the year and CO2. Let's look at another example. So here's an example of car weight versus mileage. So the computer readout here shows the regression analysis for the weight of a car versus gas mileage. Let's interpret R and R squared, and let's conduct a hypothesis test. So first thing, notice that R is negative 0.8666. So what that tells us is that as the weight increases in cars, there is a tendency for the mileage to decrease. That's what the negative is. When one goes up, the other tends to go down. R squared is 0.75. So what that tells us is there's going to be a lot of variation, possibly, in gas mileage for all cars. On the other hand, if you look at the class of cars at a specific weight, then the variation in mileage for that weight class of cars is going to be reduced by around 75%. So that tells us if we know the weight of the car, we have a much better handle on what the gas mileage might be. The p-value is less than 0.0001. So remember, the null hypothesis was that the correlation is equal to 0, and the alternative hypothesis is the correlation is not equal to 0. Since the p-value is so ridiculously small, we don't even need to look at an alpha. It's smaller than any alpha that any reasonable person would use. Then we can say that we have very strong statistically significant evidence to support the claim that there is a correlation between car weight and mileage. So here's another example. This readout shows a regression analysis for wine consumption per capita in cities and the city's violent crime rate. So notice here the correlation is 0.2606, and R squared is around 0.07. Notice that's small. That tells us that if we're told what the wine consumption is, and we want to predict what the crime rate will be for that city, then we can only reduce the variation by about 7%, having been told what the wine consumption is. So wine consumption is not a very good predictor at all of crime rate. And in particular, Notice that the p-value here is 0.13. And that's bigger than any alpha that you might use. So we don't say that there's no correlation, but what we can say is that we do not have statistically significant evidence, or there is insufficient evidence to support the claim that there is a correlation between wine consumption per capita and the crime rate. So here's another example. And for this example, we're going to be looking at religion versus crime. So the table below shows the violent crime rate and the percent of citizens who attend church regularly. What can be concluded at the 0.05 level? So here's the crime rate. Here's the percent that attend church. The question is there a correlation? Okay, so to decide if there's a correlation or not, we have data, and we can use a calculator. I'm going to use the TI-84 Plus to figure it out. So here's the calculator. And to find out about correlation, I go to Stat. Then I hit Enter on Edit. Let us clear out L1 and L2. And then in L1, I'll put the crime data. So that's 85, enter, 72, enter, 64, enter, 93, enter, 54, enter, and 60, enter. For L2, I'll put the church data, 21, enter, 17, enter, 27, enter, 14, enter, 43, enter, and then finally 22, enter. Then I go to Stat, Tests. I'm going to use the up arrow until I get to Lin, Reg, T-Test. And I hit Enter. It asks for our X list. L1 is what I want. It asks for our Y list. L2 is what I want. Freak is always 1. And let's test the hypothesis that the correlation is not equal to 0. And I just scroll down to Calculate and hit Enter. And this gives us everything we want for now. Notice that we have a few things. One is, the biggie is the p-value. The p-value is 0.08. If I'm going to use a level of significance of 0.05, then 0.08 is larger than 0.05. So we fail to reject the null hypothesis. We don't have statistically significant evidence. There is insufficient evidence to make a conclusion about whether or not there is a correlation between crime rate and church-going rate. Just a few other things. If I scroll down a little bit more, notice we have A and B. A is going to be the y-intercept for the line. B will be the slope. So the equation of the line is 61 minus 0.5187x, about. I have more. I have S, which I'm not really going to be talking about today. I have R squared, which is about 0.58. So what we can say is that, at least for our sample, that if we happen to know the crime rate, then the variation in church-going rate is reduced by about 58%. Notice that R is negative 0.76 about. That's actually not that small of an R. What's going on here, the reason why we failed to reject the null hypothesis, is that our sample size was so small. And if you have a sample size of 6, then you're usually going to fail to reject the null hypothesis. So that's why I'm not too surprised that even though I have an R that's close to -1, I still fail to reject the null hypothesis. So now let's go back to our PowerPoint. Okay, so here's the PowerPoint. I want to talk about residuals briefly, which is basically the math behind the correlation. The residual is the difference between the y value of the point and the y value of the line. So here I've drawn the line, the regression line, and all these little blue dots, these guys are the data points. Notice that the data points are not right on the line. So the difference between the data point's y value and the line y value, directly below or directly above that point, that difference is called the residual. So it's how far off the line is from predicting that particular point's y value if you know its x value. That's the residual. So now let's talk about the least squares regression line. So first, the least squares regression line is the line that has the smallest sum of the squares of all the residuals. Often we'll write y with a little hat on top of it because it's different than the y value of the point. It's a predicted y value. And that's equal to a number, I'll call it b0, plus another number, we'll call it b1, times x. Unfortunately, very few people actually almost never see it called mx plus b. When we're talking about lines and statistics and regression analysis, it's either b0 plus b1x, or the calculator we saw was a plus bx. So you got to be a little careful with your lettering system. The slope of the line, notice that's b1 here, is the rise over the run that you're used to. And let's see what that means. If we think about the run always being 1, for example, that means if x changes by 1, then y tends to change by whatever the slope is. And the y-intercept is the value of y when x is 0. So we'll have some examples to talk about what that means. So here's an example. A study was done to look at the relationship between packs of cigarettes smoked per day and how long a person lives. The equation of the regression line is y hat equals 84 minus 3x. So first, let's use the regression line to predict how long a person who smokes 4 packs a day will live. This is actually a really easy question. All we need to do is take this 4, that's packs of cigarettes a day, which was x, and plug it in for x. Notice 3 times 4 is 12. 84 minus 12 is 72. So what we can say is that we would predict that somebody who smokes 4 packs a day is predicted to live to about 72 years old. Notice we're only predicting, we're not saying that this is how long they are going to live. They could die tomorrow, they could live to 100, but our best estimate would be 72 years old. Let's interpret the slope. So first, the slope is equal to -3. That's always the number in front of x is the slope. And you could think of that as -3 over 1. So that means we're rising -3, or we're going down 3 if we run 1. Well, running 1 means a pack of cigarettes smoked. So that means that a group that smokes 1 more pack of cigarettes per day compared to another group tends to live on average about 3 years less. Notice that does not tell us, just from looking at data and regression analysis, it does not tell us that cigarette smoking causes you to live a shorter life. The causation you get with biology, not just with statistics. You actually have to have more than just the data. So now let's interpret the y-intercept. So remember, the y-intercept means if x is 0, then the y-intercept is the value of y. Notice if x is 0, then the y-intercept is 84. X being 0 means that they're smoking 0 packs a day. So that would mean that we would predict that the average lifespan for non-smokers, smoking 0, so the average lifespan for non-smokers is predicted to be 84 years old. Let's look at another one. A realtor is looking at the relationship between the year and the population in thousands of South Lake Tahoe. The equation of the regression line is y hat equals negative 975 plus 1 half x. So first, use the regression line to predict the population in the year 2000. So that means just plug in 2000 in for x. A half of 2000 is 1000. Negative 975 plus 1000 is 25. Notice that these are in thousands. So that tells us that in the year 2000, we would predict that the population of South Lake Tahoe to be around 25,000 people. Now let's interpret the slope. Notice the slope is 1/2. So we could think of 1/2 as being 1/2 over 1. And remember, this is the population in thousands. So that tells us that for every year that has gone by, there has tended to be an increase in population in a half of 1,000, or about 500 people. Let's interpret the y-intercept. Now the y-intercept is negative 975. So this one is a tough one. In this case, the y-intercept is completely meaningless because it doesn't make any sense at all for the population of South Lake Tahoe to be negative 975,000 people in the year 0. That's just silly. In fact, whenever you're making a prediction, you always have to make sure that the number that you're plugging in for x should be not that far from the data values used to come up with the equation of the regression line. So I will just tell you the data values I used for this regression line were somewhere between the year, I think it was around 1960 and 1995 or so. So 2000 isn't that far. It might make some sense to use it as a prediction. But the year 0 is so far away from the data values. And in fact, if you know anything about South Lake Tahoe, it's such a cold, snowy place that in the year 0, there were no permanent residents here. It's just too cold to live here in the wintertime. Okay, so we can't interpret the y-intercept, and that's often the case. The slope you can always interpret, but the y-intercept often doesn't have any meaning at all. Okay, let's look at another example. This example says data was taken to see the relationship between the price that a motel charges and the number of rooms that are filled. The data are shown below. Predict the number of rooms filled when the motel charges $80 per room. Then perform a regression analysis. So what I'm going to do is I'm going to use the calculator. So let's do that. Okay, so here's the calculator. What I do is I go to Stat, I go to Edit. Let's clear out L2 and L1. Okay, in L1, I put in the price, so 40, enter, and then the last one was 110, enter. And now for L2, I put in rooms. I have 92. And then the last one was 35, so I hit enter on 35. And now let's hit Stat, tests. I scroll up until I get to lin reg t-test. Hit enter. X list is L1, Y list is L2, frequency is 1, row not equal 0 sounds good. And then go to calculate and hit enter. So notice a bunch of things. So the p-value is 3.17 e negative 8. That means that it's 0.000000317. That's tiny, tiny, tiny. So there's a very, very strong statistically significant evidence to say that there is a correlation between price and number of rooms. So then I'm going to scroll down a little bit more, and I get A and B. B is a slope, negative 0.69 about, or negative 0.7. So remember that we're looking at price versus rooms. So what that tells us is that on average, for every dollar the room rate is increased, there tends to be a drop in the number of rooms rented or checked out in the hotel by about 0.7. Okay, it doesn't have to be a whole room, because these are averages. A is 117. Now that's not that meaningful, because we're thinking about owning a motel or a hotel, and it doesn't really make any sense to charge no money for our hotel and say that we would expect to have 117 rooms used. So it's probably not very meaningful to talk about the y-intercept in this case. Notice that the correlation is about negative 0.95. That's pretty strong, pretty close to negative 1. And R squared is about 0.9, so 90% of the variation in the number of rooms that are used at our hotel can be predicted or reduced by knowing the price of the room that we charge. Let's do one more example before we're done. Okay, so here's the final example. Data was taken to see the relationship between the age when a person has their first kiss and the age when virginity is lost. Predict the age of virginity for a person who experienced his or her first kiss at age 15. Then perform a full regression analysis. So here's kiss and virginity. We have our data, and we can go right to the calculator and start plugging that in. Okay, so here's the calculator. I go to Stat, Edit, and let's clear out L2 and L1. In L1, I'll put the age of first kiss. So we have 12. Enter. And the last one I put was 18. And now let's go to L2, and I'll enter the virginity ages, the age at which people lost their virginity. We have 14. Enter. And then finally 23. Enter. Now let's go to Stat, Tests. Scroll up until you get to lin reg t-test. Hit enter. So L1 is the X list, L2 is the Y list, freak is 1, row not equal 0 is what we want, and let's go to calculate. Alright, so our p-value is 0.01 about. That's less than your standard alpha, 0.05. So we can say that there is statistically significant evidence to support the claim that there is a correlation between the age at which people experience their first kiss and the age at which they lose their virginity. Notice that A and B are 6.9 about, and about 0.8. So B is about 0.8. So that tells us for every year people tend to wait to get their first kiss. They tend to lose their virginity about 0.8 years later. Also, this one doesn't make any sense at all if you're looking at the y-intercept, because it doesn't really make sense, let's hope not, that the first kiss that people experience, and I'm talking passionate kisses, is at age 0 when you're born. That's just sick. So that's not something that makes any sense. And if you look at the data range for first kiss goes from 12 to 18. 0 is very far from those numbers. So we're not going to interpret the y-intercept. If you look at the correlation, R was about 0.63, and R squared was about 0.4. So 40% of the variation at which people tend to lose their virginity can be reduced if you happen to know when they experience their first kiss. And then finally, if you want to predict when a 15-year-old will lose their virginity, again, we don't know for sure they're going to lose at this age. We just plug in. So we see that we have a plus bx. So we're going to take, let me scroll up a bit so we can see a again, about 6.9 plus 0.8 times x, which is 15. So let's actually type that in. 6.9 plus 0.8 times 15. 6.9 plus 0.8 times 15. Enter. And that's 18.9. So what we can say is that for the group of people who experience their first passionate kiss at age 15, our best prediction for their average age at which they lose their virginity is almost 19 years old. So hopefully you understand regression analysis a little better than you did before we started this video. And if you have any questions, if you're my student, please ask me and I'll help you out. Send me an email, come to my office, or whatever. If you have another instructor from wherever, make sure that you do get help and figure out how to do all this stuff. Because regression analysis is quite important and can be difficult. So have a good morning or a good night, good day, whenever it is for you. And thank you again for watching.